Okay, thank you all for coming, and welcome to the Masters of Science Defense in Ocean Mapping for Christina Fandel. Just a few words about Christy before we get started. She received her BS with honors, I noted, in geology from the College of Charleston in 2010 and came to us shortly thereafter in the fall of that year. She's been very busy over her time here. Part of her activities have been involved in field work, and including the work that she'll be discussing today. An interesting story about Christy with respect to this experiment is that she came to us and said, this is what I want to do. And she said, I want to study pockmarks. And she really has been, and I basically said, well, what's a pockmark? I didn't even know what it was. I think many of us didn't know what it was. But she basically guided much of the work that we did. I feel like I was sort of being dragged along in her wake. And so it was largely driven in part by Christy. She also spent some time at sea on cruises, particularly for the Lava Sea on the Healy in the Arctic, and also on the Ron Brown, I guess, off the coast of South Carolina. And she spent some time with us at New River doing some nearshore work. She'll be pursuing options when she's finished. She has some opportunities here at CCOM looking at Sandy hurricane impacts. Okay, I want to introduce the Thesis Committee, including myself. There is Diane Foster from the Department of Mechanical and Ocean Engineering, Jim Irish from the Graduate Program in Ocean Engineering. Everybody knows Jim. And of course, Larry Mayer is the other member for committee. Okay, she's going to give about a 45 or so minute talk. Then we'll have questions from the audience for a few minutes, and then we'll excuse the audience, and then we'll sit with Christy and talk about her thesis. Okay, thank you.
Thank you for attending my thesis research presentation. Today I will be discussing observations of pockmark flow structure in Belfast Bay, Maine. I'd first like to start by thanking NOAA for graciously funding this work. In this presentation, I'll first give you a general introduction to what pockmarks are, as well as the previous research that's been completed concerning flow over these depressions. And then I will present the three goals which I sought to answer in this research, as well as the methods I used to do so, and then conclude with the results of this research. So what are pockmarks? Pockmarks are often referred to as seafloor craters because they form large depressions in the seafloor. And they cover a wide range of sizes, ranging from less than a meter to several kilometers in diameter, and less than a meter to several tens of meters in relief. The primary mechanism of formation has been attributed to the release of fluid and gas from the underlying sediment, either through an evolutionary or instantaneous event. Here is a bathymetric image obtained within the Belfast Bay pockmark field in Maine, and we observed that these pockmarks occur both singularly as well as in chains, and transition from more spherical in the northern region to more elongated in the southern region. One of the important observations to note about pockmarks is that they're not restricted to a specific type of geological setting, and they're found in a wide range of environmental settings, including deltas, as off the coast of Alaska, in freshwater lakes, as in New Zealand, in areas of petroleum production, like off the coast of mid-Norway, as well as in previously glaciated areas like the Gulf of Maine. The primary goal of this research project was to examine the flow structure over the pockmarks, and therefore it's important to explain to you why it's important to study the vertical structure and circulation patterns within these depressions. As you can see from these ROV images obtained within an individual pockmark located off the coast of mid-Norway, many pockmarks are associated with an abundant biological community. So understanding how the flow circulates and moves throughout these depressions will better constrain ecological models that predict nutrient and faunal distribution in these depressions. Another important reason to study pockmark flow structure is that it will better constrain our estimates of pockmark ages, which is a major area of limitation in pockmark research. By obtaining current observations close to the bed, we can predict, or better predict, sedimentation and erosion rates within these areas, as well as gain a better understanding of flow over large roughness elements, which, as you can see from this bathymetric image, these pockmarks form very large roughness elements on the seafloor. Despite the importance of understanding the flow structure over pockmarks, only 3 studies have addressed the flow patterns and circulation patterns over pockmarks. The first was completed by Manley et al. In 2004 within a shallow pockmark in Lake Champlain, Vermont, with a length to depth ratio of 10. They completed long-term current and temperature observations using a subsurface mooring positioned at the center of the pockmark. This subsurface mooring was equipped with a downward-looking acoustic Doppler current profiler, a vertical temperature chain, and stereo cameras at the base to document any periods of sediment suspension. An interesting observation they made from their measurements was this large-scale overturning and mixing event highlighted by the red box. This event was due to increased wind stress at the surface, pushing waters north and allowing the deep bottom waters to upwell towards the surface. Here we have the temperature data collected in September as a function of time on the x-axis and depth on the y-axis, where the horizontally dashed line denotes the approximate depth of the rim. We observed that over multiple periods, there's homogeneous temperature profiles above and below the rim, which suggests that the water above and below the rim is actively being circulated throughout the depression. The second study was completed by Hammer et al. In 2009, and they obtained observations of the vertical component of velocity at multiple locations within a deep pockmark located in the inner Oslo Fjord, Norway. These observations were obtained at the locations denoted by the red dots, and the strongest positive vertical velocities were observed at the center and downstream sites, although positive vertical velocities were observed at all locations within the pockmark. They were able to regenerate these observations using two-dimensional numerical modeling of flow over a pockmark. Here, this white streamline denotes the geometry of the depression, and the warmer colors show the higher velocity, positive vertical velocities. Again, the strongest positive vertical velocities are observed in the center of the pockmark that propagate vertically upwards. They concluded that the net sedimentation rate within these pockmarks is going to be based on a balance between the reduction in horizontal flow within the pockmark and the strong updraft they observed within these depressions. The third study was recently completed by Brothers et al. In 2011, and they completed 2- and 3-dimensional numerical modeling of flow over a sample pockmark. They noted areas of enhanced turbulence at the rim and suggested that this may lead to erosion over time and explain the elongated morphology of many of the pockmarks in Belfast Bay. One of the observations they did not note was the relative dependence of the pockmark geometry on the observed circulation pattern. In the image to the left, the length to depth ratio of the pockmark is 18, which characterizes a rather shallow pockmark. And they observed contour following currents in this depression. Whereas as the relative length to depth ratio decreased, denoting a deeper pockmark, they observed the formation of a recirculation cell within the depression. And this concept of the dependence of a pockmark geometry on the flow circulation will be a concept that I discuss later on in this presentation. So from all of these previous studies, they all suggested that future studies obtain current observations over pockmarks within various pockmark fields, as well as examine the relative dependence of pockmark geometry on the vertical flow structure. So the primary goal of this research was, again, to examine the flow structure over pockmarks. We first wanted to examine our observations to determine whether or not our vertical profile over the pockmarks could be characterized by mixing or non-mixing. Previous studies suggest that the flow structure over, or the vertical structure over pockmarks is characterized by the active overturning of water above in the rim. So we wanted to examine whether our observations were consistent with those previously obtained. The second goal was to characterize the depth averaged directional structure observed over each pockmark. Previous studies suggest both contour following and recirculation cell formation within the pockmark may characterize the circulation patterns over pockmarks. We wanted to examine if any pre-existing conceptual flow model was consistent with our observed results. And thirdly, we wanted to examine the influence of near-bed sediment transport acting to modify these pockmarks over an extended period of time after formation. And we examined this by looking at the force balance on an individual sediment grain. Now, I've previously presented on the evidence for mixing and circulation patterns, so the majority of this presentation will focus on the sediment transport aspect of this research. This study was completed in the Belfast Bay Pockmark field, which is located along the central coastline of Maine in the northeastern quadrant of Penobscot Bay. Belfast Bay is characterized as a shallow estuarine environment, and the morphology of the pockmarks transitions from more spherical in the northern region to more elongated in the southern region. The pockmarks sampled in this study were located in the northern and southern region and will be referred to as such throughout the rest of this presentation. The northern pockmark had a slightly more spherical morphology with a length to depth ratio of 4.7, and the southern pockmark had a slightly more elongated morphology with a length to depth ratio of 3.7. In order to address our goals, we obtained observations of the bathymetry, current, and sediment characteristics over both pockmarks. This study was completed in late July 2011 aboard the RV Cochico. A preliminary bathymetric survey was completed over both pockmarks to examine the local bathymetry as well as determine where we wanted to position the ADCP mounts within each pockmark. The bathymetry study was completed using an Odom THP 200 single beam echo sounder operating at 200 kilohertz, and submeter precise positioning was obtained using an OmniStar differential GPS. In the bathymetrics maps to the right, the northern pockmark is shown in the upper panel and the southern pockmark is shown in the lower panel. The northern pockmark had a slightly more spherical shape when compared to the more elongated southern pockmark. The northern pockmark was located in 24 meters water depth and had an approximate diameter of 45 meters and 12 meters of relief, whereas the southern pockmark was located in 24 meters of water with a diameter of about 80 meters and had 17 meters of relief. Vertical current observations were obtained at the rim and center of each pockmark for a 42-hour sampling period. The current observations were first obtained over the northern pockmark and then later obtained over the southern pockmark. The center current meter mount was equipped with an upward-looking 300 kilohertz ADCP, acoustic Doppler current profiler, averaging data over 5-minute intervals, and an aqueduct current meter averaging data over 1-minute intervals. The ADCP obtained vertical observations of the velocity structure beginning at 2.5 meters above the bed, and the aqueduct current meter obtained measurements at 0.7 meters above the bed. In the images to the right, we see a north-south profile across the northern pockmark in the upper panel and the southern pockmark in the lower panel, as well as the approximate location of the center current meter mounts and rim current meter mounts along each pockmark. The center current meter mounts were actually positioned slightly northeast of the center of either pockmark within the northeastern quadrant of the pockmark and were oriented at a significant tilt. However, this orientation was accounted for internally during data acquisition by the ADCP. Multiple CTD casts were also obtained over the center of either pockmark to examine the time-varying structure of the vertical current or vertical profile. These CTD casts were obtained approximately every 2 hours for a complete tidal cycle, as denoted by the black and gray dots along this tidal wave. At the end of the survey, multiple sediment grab samples were obtained at the rim and center of each pockmark to later examine the grain size distribution and water content at each location. Here we have the depth averaged horizontal current magnitudes obtained over the northern pockmark on the left and the southern pockmark on the right as a function of time on the x-axis. The horizontal current magnitudes were averaged over the surface, mid, and deep portions of the water column, delineated by the average depth of the thermocline, 8 meters, and the depth of the rim. This upper panel shows tidal elevation as a function of time, and the lower 3 panels show the depth average current magnitudes obtained at the surface, mid, and deep water column. The surface currents showed significant spatial and temporal variability and typically oscillated around 10 centimeters per second. The mid-water flow was had a strong tidal signature and again oscillated around 10 centimeters per second. Below the rim, the depth average currents were low and never exceeded 10 centimeters per second. But again, a slight tidal oscillation was observed at this location, or at this depth average. Now, to examine our first goal, we looked at the time, or the CTD casts obtained over each pockmark, as well as the depth average vertical velocities below the rim, to examine whether or not our observations were consistent with a well-mixed water column. Here we have the temperature and salinity profiles obtained over the center of the northern pockmark on the left and the southern pockmark on the right. Again, the upper panel shows tidal elevation as a function of time, where the black and gray circles denote the times at which the CTD casts were obtained in the lower panel. Salinity data is shown on the left panel, and temperature data is shown in the right panel. Both profiles over both pockmarks show surface variability in the salinity profile, most likely due to freshwater input, and in the temperature profile, most likely due to diurnal heating and cooling throughout the day. Interestingly, we observed uniform temperature and salinity profiles over both pockmarks below a depth of about 15 meters, which is indicative of a well-mixed water column. This suggests that water below the rim is actively circulating and mixing with the water above the rim to create a homogeneous profile. Further evidence for mixing came from bottom-mounted temperature sensors at the rim and center locations of the current meter mounts. This second panel shows the temperature data obtained at the rim and center current meter mounts. The rim data is shown in red, and the center data is shown in blue. The lower panel shows the depth average vertical velocities below the rim as a function of time on the x-axis. The highlighted yellow region shows a 0.3 degree Celsius temperature rise recorded both at the rim and center of the pockmark. This is indicative of mixing of water to create a homogeneous profile. Interestingly, the temperature rise at the rim occurred slightly after the temperature rise at the center of the pockmark, which suggests that this mixing event was actually initiated within the depression. During this temperature rise, we also observed significant positive vertical velocities followed by a strong downwelling event, providing further evidence that mixing is occurring within these depressions. So from our observations of uniform temperature and salinity profiles below the rim, as well as this nearly simultaneous temperature rise observed over the northern pockmark, we suggest that the flow is actively being interacted above and below the rim. Now, to examine the directional structure over each pockmark, we wanted to classify the circulation pattern by examining the directional structure over each pockmark. Here we have the horizontal velocity direction profiles collected over the center of the southern pockmark. The upper panel shows the tidal elevation, where the highlighted regions denote the hour-long interval over which the velocity data being displayed in the lower panel is being averaged. Flooding tidal conditions are shown in purple, and ebbing tidal conditions are shown in green. The lower panel shows direction along the x-axis, where the vertically dashed gray line denotes 0 degrees. Elevation is shown on the y-axis, and the horizontally dashed orange line shows the depth of the rim, and the horizontally dashed black line denotes the depth of the bottom of the pockmark. So overall, we observed significant directional changes from surface to depth, specifically below the rim. During the flooding tide, these directional changes occurred more gradually from surface to depth, whereas during the ebbing tide, these directional changes occurred more abruptly, typically at about 10 meters above the bed. During the flooding tide, these directional changes from surface to depth were typically on the order of 50 to 90 degrees, whereas during the ebbing tide, these directional changes typically exceeded 90 degrees and often approached complete flow reversal near the bed. To examine the depth average directional profiles as a function of tidal phase, I have created a movie and MATLAB that shows the time-varying currents observed over the center of the southern pockmark. This upper panel shows the tidal elevation as a function of time, where the highlighted red bar denotes the hour-long interval over which the velocity data in the lower panel is being averaged. In the second panel, the x and y axes denote the relative u and v components of velocity, and the z-axis shows elevation in meters. The horizontally dashed orange line again denotes the depth of the rim, and this gray vector is a scale representing 25 centimeters per second. So as we watch this video, focus your attention on the lower 15 meters of the water column, or the flow below the rim, where we observe the most significant degree of directional change from surface to depth. Again, during the flooding tide, we expect to see a lesser, more gradual degree of change from surface to depth, typically on the order of about 90 degrees, whereas during the ebbing tide, we expect to see complete flow reversal at the base that occurs very abruptly at about 10 meters from the bed. So during flooding tide, we see about 90 degrees of rotation with depth, whereas during the ebbing tide, these directional changes occur more abruptly and exceed 90 degrees below the rim. Again, during flooding tide, the rotational changes occur more gradually, typically on the order of 90 degrees, whereas during the ebbing tide, abrupt changes are observed approaching 180 degrees and complete flow reversal at the bed. Higher velocity flows during the flooding tide rotate gradually about 90 degrees from surface to depth, whereas during ebbing tide we see flow reversal near the bed. Again, these gradual changes during the flooding tide, typically on the order of 90 degrees. So these observations of a greater degree of rotation during the ebbing tide that occurs more abruptly are qualitatively consistent with circulation patterns predicted by cavity flow. Cavity flow describes the flow over a rectangular depression and is typically defined by the time mean behavior of the shear layer. And the shear layer is the layer of flow that forms as the flow separates over the cavity due to the geometry of the depression. The time mean behavior of the shear layer has been found to be strongly dependent on the length to depth ratio of the cavity and subdivides cavity flow into two flow regimes, closed cavity flow and open cavity flow. Closed cavity flow typically occurs in shallower depressions with length to depth ratios greater than 9 and is characterized by contour following currents. Whereas open cavity flow typically occurs in deeper cavities with length to depth ratios less than 6 and is characterized by the formation of a large recirculation cell within the depression. Because the length to depth ratio of the northern and southern pockmarks are both less than 6, we would expect the circulation patterns within these depressions to be qualitatively consistent with open cavity flow circulation. Now, as expected, the relative location of the ADCP current meter mount within the pockmark is going to affect the observed degree of rotation we observe from surface to depth. If the ADCP mount is located further downstream, we expect a lesser degree of rotation from surface to depth than if the ADCP mount is located further upstream, where this recirculation cell has completely formed and we expect to see flow reversal near the base. If you remember, the location of the ADCP current meter mounts within our depressions, within our pockmarks, were located within the northeastern quadrant, or at about 0.6 the length of the cavity from the leading edge during the flooding tide, and 0.4 the length of the pockmark from the leading edge during the ebbing tide. Therefore, we would expect to see a greater degree of rotation during ebbing tidal conditions than during flooding tidal conditions, where this recirculation cell has completely formed and we observe flow reversal near the base. This is consistent with what we previously showed, that a greater degree of rotation from surface to depth is observed on the ebbing tide, approaching 180 degrees with depth, than during flooding tidal conditions, where the change in direction from surface to depth was more on the order of 90 degrees. Another defining characteristic of open cavity flow is the growth of the shear layer with distance downstream. Therefore, we would expect to see a greater shear layer thickness during the flooding tide due to the location of the ADCP mount further downstream than during the ebbing tide due to the location of the shear meter mount, ADCP mount further upstream. And we approximated the shear layer thickness using vorticity thickness and did show that the estimated shear layer thicknesses were thicker during flooding tidal conditions. This suggests that pockmark flow circulation may, to a first order degree, be similar to cavity flow circulation. Again, recent modeling by Brothers et al. In 2011 shows contour following currents over the shallower pockmark, which is consistent with closed cavity flow circulation occurring in pockmarks with length to depth ratios greater than 9 cavities. And the numerical simulations of flow over a deeper pockmark with length to depth ratio of 5 shows the formation of a recirculation cell within the depression, which is consistent with open cavity flow circulation, which is characterized by cavities with length to depth ratios less than 6. Therefore, we suggest that to a first order degree, pockmark flow circulation may be modeled by cavity flow. The third goal of my research was to examine whether or not near-bed sediment transport may be acting to modify pockmarks post-formation. Again, if you remember, the morphology of the pockmarks in Belfast Bay transitioned from more spherical in the northern region to more elongated in the southern region, as the proximity to this narrow channel to the west of Islesboro Island is approached. Therefore, we would expect to see a greater amount of sediment transport, predicted periods of sediment transport, along the southern pockmark as compared to the northern pockmark. In conjunction with our current observations, we also obtained sediment samples at the rim and center of each pockmark to assess the grain size distribution and water content at each location. The water content was measured as a function of the wet and dry weight of the sediment and was obtained by taking a sample, weighing the wet sample, then oven drying it for 24 hours at 75 degrees Celsius, and then re-weighing it to calculate the water content. Typically, our water content values varied by less than 5%. However, we saw a greater degree of variation from samples obtained at the center of the southern pockmark. And this range of measured water content values will present itself as uncertainty in our estimates of the critical stress parameter. Here is the grain size distribution obtained over at the rim and center of each pockmark as a function of grain size on the x-axis and percent by volume on the y-axis. Our median grain diameter was 7 microns, which would classify our sediment as fine silt. Now, if greater than 10% by mass of a sample is less than 63 microns, the sediment is expected to exhibit cohesive properties. And these cohesive properties act to bind individual sediment grains together through electrostatic forces or organic matter, and therefore must be accounted for in estimates of the critical stress parameter. Because the majority of our sediment is less than 63 microns, we expect our sediment to exhibit cohesive properties. To estimate whether or not sediment transport is occurring, we require observations of the horizontal velocity profile above the bed. And in order to determine whether or not an individual grain diameter or individual grain suspended in the flow is expected to remain in suspension or settle towards the seafloor, requires observations of the vertical velocity component. Here we have the depth averaged horizontal current magnitudes and vertical velocities obtained in depth averaged over the midwater column in red and below the rim in blue. The depth averaged midwater current magnitudes show a strong tidal oscillation that oscillates around 10 centimeters per second. Comparatively, the midwater vertical velocities are low and rarely exceed 0.5 centimeter per second. Note that the majority of the period is characterized by negative vertical velocities, which would characterize, in general, conditions favorable to the settling of fine-grained material. Below the rim, the depth average current magnitudes are much lower and never exceed 10 centimeters per second. Comparatively, the depth average vertical velocities are strong and generally comparable in magnitude to the horizontal flow. Again, we observed that the majority of the sampling period is characterized by negative vertical velocities, which would characterize conditions in general favorable to the settling of material. Now, to determine whether or not an individual cohesive sediment grain is expected to move, it is described as a force balance acting on the particle. So if the drag and lift forces induced by the flow exceed the gravitational, frictional, and cohesive forces acting to keep an individual grain in place, we expect sediment transport or sediment movement to occur. And this balance of forces is typically parameterized using the non-dimensional Shields parameter, which is a function of the sediment and water density, the acceleration due to gravity, and the median grain diameter, as well as this term known as the friction velocity, which characterizes the hydrodynamic shear in the boundary layer. And this term is typically approximated, assuming turbulent flow conditions, using a logarithmic velocity profile of the horizontal velocity. So in order to determine whether or not we can apply a logarithmic velocity profile to our horizontal velocity data to predict the current velocities in the near bed region requires us to characterize the horizontal velocity profile as either non-logarithmic or logarithmic. Here we have examples of the horizontal velocity data obtained over the center of the southern pockmark as a function of magnitude on the x-axis and depth on the y-axis. During our sampling period, we observed periods characterized as non-logarithmic, logarithmic, and dual logarithmic. And when a single logarithmic layer was observed within the horizontal velocity profile, an estimated friction velocity could be achieved. Interestingly, we saw regions of dual logarithmic layers within our velocity data, which was also observed by Kristen Caldwell in 1982. And this is indicative of roughness-induced form drag influencing the local flow regime. So in other words, turbulent processes occurring further upstream, most likely due to flow over other pockmarks, is influencing the local flow regime over our sampled pockmarks and adding increased stress to the total boundary stress. Again, like I said, when a single logarithmic profile is observed, a friction velocity term may be estimated using this equation here, which assumes hydrodynamically smooth flow and is a condition that we satisfy. Once we have our estimates of the hourly average friction velocity, we may then take these parameters and input them into our Shields parameter to come up with a non-dimensional estimate of the bed shear stress. The question then becomes, when do these hourly average estimates of the Shields parameter exceed some critical value? For non-cohesive sediment, the critical Shields parameter is primarily a function of the grain size. However, for cohesive sediment, the critical Shields parameter must account for the cohesive nature of the sediment. In this study, we approximated the critical Shields parameter using a theoretical model by Dade et al. In 1992. Dade et al. Approximate the cohesive force acting between individual sediment grains using the yield stress of the sediment, which is a stress parameter that defines a limit stress above which the sediment begins to flow. And this yield stress parameter is found within the model within this FA over FS term, which characterizes the cohesive forces acting in the vertical relative to the submerged weight of the grain. In this study, we approximated the yield stress using our measured water content values based on an empirical formula developed by Hopner in 2001. Here are our estimated critical Shields parameters obtained at the rim and center of each pockmark, as well as our measured water content values and estimated yield stresses. As expected, the greatest range in our critical Shields parameter occurs at the center of the southern pockmark due to the wide range of water content values measured at this location. Now, by comparing our hourly average Shields parameter to these critical values, we'll provide some insight as to whether or not we expect incipient motion to occur. If the hourly average Shields parameter is greater than the critical Shields parameter, we expect incipient motion to occur, whether well, if it's not greater than the critical shields parameter, we do not expect sediment transport to occur. Here are our hourly average estimates of the shields parameter as a function of time on the x-axis and shields parameter on the y-axis. Shields parameter estimates obtained from the center of the pockmark are shown in blue, and those obtained at the rim are shown in red. The critical shields parameters are shown as horizontally dashed lines, where the error bars denote the range of expected critical shields parameters based on the measured water content values. So at the center of either pockmark, denoted by blue dots, the hourly average shields parameters never exceed the critical value, and therefore we would not expect sediment transport to be occurring within the center of these pockmarks. However, at the rim of either pockmark, the hourly average shields parameter periodically exceeds the critical value and suggests that incipient motion is occurring during these time periods. The greater frequency of shields parameters exceeding the critical value observed over the southern pockmark may be related to the higher velocity flow in this region. Now, to determine whether or not an individual sediment grain is expected to remain in suspension or fall towards the seafloor, we approximated the minimum grain diameter under terminal settling conditions. The terminal settling velocity is described as a force balance acting on the grain in the vertical, and is reached when the submerged weight of the grain equals the drag induced by the flow. In this study, we rearranged Stokes' terminal settling law to approximate the minimum grain diameter capable of remaining in suspension under the observed depth average vertical velocities, or the grain diameter such that the submerged weight of the grain equals the drag induced by the observed vertical velocities. Now, the minimum grain diameter was only calculated during periods of positive depth average vertical velocities, because during periods of negative depth average vertical velocities, the submerged weight of the grain was much greater than the drag induced by the flow, and therefore the grain is expected to settle towards the seafloor. It's important to note that this equation was developed for non-cohesive sediment, so does not account for the flocculation of material, which is expected to occur in our setting due to the cohesive nature of our sediment. Nonetheless, by comparing these minimum grain diameters to the median grain diameter observed at the bed, provides some indication in a general time average sense whether or not an individual particle is expected to remain in suspension or settle towards the bed. So, if the estimated minimum grain diameter is greater than the median grain diameter, the minimum grain diameter is expected to remain in suspension under the observed positive depth average vertical velocities. However, if the estimated minimum grain diameter is less than this median grain diameter, the grains are expected to settle towards the seafloor, assuming the grains in suspension are the size of the median grain diameter. Here we have the hourly average estimates of the minimum grain diameter as a function of time on the x-axis and grain diameter in microns on the y-axis. Minimum grain diameters estimated at the rim are shown in red, and minimum grain diameters estimated at the center are shown in blue, again only during periods when positive depth average vertical velocities were observed. The median grain diameter is shown as a horizontally dashed black line along the northern and southern pockmark, or of the northern and southern pockmark. At all times when positive depth average vertical velocities were observed, the estimated minimum grain diameter was always greater than the median grain diameter, and suggests that during these periods, any suspended sediment less than or equal to the minimum grain diameter will remain in suspension. The highlighted yellow regions denote periods during which incipient motion is predicted to occur along the rim of either pockmark. During 2 of these time intervals, the estimated minimum grain diameter was greater than the median grain diameter, and suggests that during these periods, sediment less than about 90 microns would be unable to settle towards the seafloor. Incipient motion was never predicted to occur at the center of either pockmark. However, when positive depth average vertical velocities were observed at the center location, the minimum grain diameter was much greater than the median grain diameter, Therefore, any sediment suspended above the bottom of the pockmark may potentially remain in suspension under these observed positive vertical velocities. So our estimates showing incipient motion to occur along the rim of either pockmark in conjunction with positive depth average vertical velocities significant enough to prevent the settling of fine-grained material suggests that the near-bed sediment transport may be acting to modify pockmarks in Belfast Bay over long periods of time. Again, the morphology of the pockmarks in Belfast Bay transitions from more spherical in the northern region to more elongated in the southern region. This is consistent with our observations of a greater frequency of excess bed shear stress predicted along the rim of the southern pockmark as compared to the rim of the northern pockmark. Interestingly, this morphological transition from more spherical in the northern region to more elongated with distance offshore is also found in other regional pockmark fields, including Blue Hill Bay, Maine, and Passamaquoddy Bay, New Brunswick, and suggests that near-bed sediment transport may be acting to elongate these depressions over time. This study obtained vertical observations of the current and hydrographic structure within 2 pockmarks in Belfast Bay, Maine. We showed that during our sampling period, the vertical water column over our pockmarks is well mixed from about 15 meters to the bottom of the pockmark and may be described as the active overturning of water above and below the rim. We also showed that there was a significant degree of directional changes from surface to depth and a greater degree of directional changes during the ebbing tide, which is qualitatively consistent with circulation patterns predicted by open cavity flow. Finally, we characterize multiple periods of incipient motion along the rim of both pockmarks and suggest that near-bed sediment transport may be acting to modify these pockmarks over time. This study was the first to obtain current and hydrographic observations over 2 pockmarks of varying geometry in an estuarine pockmark field, and therefore provides valuable information about pockmark flow structure in these settings. Future studies would benefit from obtaining current observations at multiple locations within and along the rims of the pockmark to gain a better understanding of the 3-dimensional structure or flow structure over these depressions, as well as obtaining current observations during high velocity flow events such as spring tides or storm events. Our sediment transport estimations will be improved by obtaining current observations closer to the bed, as well as obtaining a better understanding of the sediment characteristics in the area. So I would like to thank NOAA for graciously funding this work, as well as my thesis committee, Tom, Diane, Jim, and Larry, for supporting me in acting as mentors throughout this process. I'd like to especially thank Laura Brothers, who was the initial inspiration for this work and has served as an academic mentor throughout this process, as well as various UNH CCOM faculty and staff members, specifically extended conversations with Jim Gardner, Val Schmidt, and Joel Johnson and Larry Ward. The fieldwork portion of this work could not have been completed without Captains Ben Smith, Captain Emily Terry, and John Hunt. You were instrumental in this work. And then many of my fellow graduate students, specifically Lindsay, Kevin, Sylvia, and Megan, and then my family and friends. I'd also like to extend a special thank you to the CCOM community as a whole. Today is almost 3 years ago to the day that I received my acceptance letter to CCOM, and attending CCOM has been a long-term academic aspiration of mine, so I'm extremely thankful for this opportunity. So thank you.
Thank you. We have some time for some questions, so please feel free to raise your hand, and I'll just let Christy call when people as she hears to.
Jim?
So were your measurements enough to tell you that sediment that was from the center bottom of the pockmark, when you had the strongest turbulence, to get actually up and out of the pockmark, or would it simply rise up in the water column and come right back down?
That's a good question. I don't know that I can answer that based on my observations, but below the rim, the vertical velocities and the horizontal velocities are comparable in magnitude. So unless the vertical velocities were significantly stronger than the horizontal velocities, I don't know that it would get out of the sediment, or out of the pockmark.
Yeah.
Monica?
Yeah, I was just wondering if you could speculate why when you showed your temperature increase and it was like 3 degrees or 2 degrees or something, it started off kind of within the pockmark near the center and then migrated to the rim. But can you speculate like what might have caused that temperature increase in the center of the pockmark? I mean, it's fine if you can't. I just was curious.
No, I'm thinking. I mean, it could be circulation induced, although you would see that at the rim first. The vertical velocities may have induced that because they were really, really strong at that below the rim. It might have acted to mix the warmer water above the rim, well above the rim, down into the pockmark.
Go back to your plot of the temperatures there.
Okay, this is going to be a Larry thing.
Back forward one.
Oh wait, the end, the conclusions. Yeah, that's right.
Okay, so the problem is the red one. The red one is the
rim.
And
the blue is
the temperature sensor and the rim ADCP was buried in the head of the instrument. So it had a very long time constant, like an hour. And then I noticed you didn't plot the beginning record too, because you see a smooth curve as the temperature cools down as it's deployed in the water. So before you start explaining that as some weird geological feature, I'd go back and look at the time constants.
Oh, you're saying that it might just be an offset?
Yes, there is an offset.
There is an offset, okay.
The question is it as big as you got there?
Well, I calibrated these temperatures to those that we observed from the CTV casts.
Because once it's down, you see the small oscillations, but if you look at the beginning, you'll see a long decay, and that'll give you the time constant for the thing, which you can then apply to this.
I see what you're saying.
To see if there is really a delay.
Okay.
But there is a difference in the two instruments. And the one in the pockmark has a temperature sensor right on the surface of the transducer, so it responds faster.
Okay.
Yeah, and if it was cavity flow, that open cavity flow that was dominating the flow, where would you expect? Would you expect the pockmark to mix first? Where's the mixing occurring?
Oh, it would occur in the pockmark.
In the pockmark.
Because the flow over it is just going with the primary direction of the tidal flow.
Are these pockmarks actively venting now, or are they relic?
There's conflicting evidence, to say the least. So a geochemical survey in 2003 towed a metal oxide sensor across the bed, and they showed no measurable quantities of methane or pore water. But a study done in 2011 did cores, and they noticed bubbling at the surface when they released the core. They measured ignitable quantities of methane, and they showed cracks at the base of the core, which they interpreted to be due to gas expansion. And these conflicting thoughts go back and forth for the past about 20 years.
Are they really conflicting?
Well, they conclude by saying the pockmark field is not actively degassing, or we do think there's evidence.
The geochemists didn't see that.
The geochemists didn't see it.
But the evidence you just said that was in the core was...
Well, yeah.
There's a difference between having methane trapped in a sediment.
Right, there's
and having
actively
a core that
venting.
expands and actively venting.
Right, I agree. So there's undoubtedly evidence for methane. Whether or not it's actively venting is what people go back and forth about.
And is there any reason to expect it to be continuous? It could be very episodic.
Right, exactly, yeah. Lindsay?
So did you find any large fauna or flora in your grab samples?
I didn't, but talking to the local fishermen, they preferentially, when the thermal conditions are good, they will fish and deploy lobster pots in pockmarks. So it suggests that there are active fauna in there. Lee?
Mine's kind of a big picture question. Can you go back to your very first couple slides in particular to show the locations of these pockmarks worldwide?
Oh, yeah.
Then you have a slide or two after that.
You can use the slide bar on the left if you want to just.
Okay.
It's there now.
I mean, there's Oslo Fjord, for instance. Keep going. Yeah, there you go. Okay, so something had to create the pockmarks to begin with, and then you were just mentioning the methane and whether or not there's actively being maintained. Your study looked more at what seems to occur within these pockmarks in terms of the type of activities and the factors. But how would you look at this and come up with an estimate of, are there going to be more or less as we go through, say, global climate change, and what's the significance of this distribution?
I think this distribution is mainly based on where these surveys have taken place. You don't notice that there aren't any in Antarctica, but people don't survey in Antarctica as often. But
Well, for instance, there aren't a whole lot around South America, aren't a whole lot around Australia, except in the very northern there, the Torres Straits. But I'm just curious about the distribution would be. And
well,
why
they're
they occur.
associated. I looked at shallow water pockmarks, but the deeper water pockmarks are more often associated with faulting or, gas from deeper within in the earth, and so they're related to faulting patterns, but I'm not sure how global.
Well, could it be just surmised, and perhaps the location and the number of pockmarks are indirectly related to the amount of exploration, say, for oil and gas?
Oh, you mean they would serve as like a proxy for where to look for gas?
Almost the other way around. If you're looking for oil and gas, and you would probably detect that there are pockmarks in existence. If you're not, then generally speaking, I guess you would not know that they may be located there. Is that, in other words, the significance of this distribution? I'm just curious.
Both of those are true.
What's that?
Both of those are true.
Yeah.
They're used quite a bit as indicated.
But the common
For
thing here is,
exploration.
these are high sediments with high organic carbon in them. So they're almost all, if not anaerobic, they're dysrobic. Very low oxygen content because they're in areas with huge amounts of organic carbon, or in areas of intermediate water, which has low organic, or doesn't have enough oxygen for it to combust the organic carbon. I think that's the common thing, except for maybe that lake.
So this
lake
isn't just where they've been detected or where people have looked for pockmarks. This may be more sediment influence then?
I think it could be sediment. It is a factor of the sediment. You need gas in order to form the pockmarks.
But following up on Lee's question, what is the source of the gas?
In my bay, they believe in my bay.
She's taking ownership.
Yeah.
That's what we want to see.
We talked about this. In Belfast Bay, the source of the gas came from coastal wetland deposits. So during the last deglaciation, when the relative sea level was a lot lower, Belfast Bay is hypothesized to have formed a coastal wetland.
So it's biogenic gas. What's the other option?
Thermogenic.
And is that feasible where you are?
We're going through a global climate change, and there's all sorts of talk about methane being released. So we're going to see a lot more pockmarks in the future.
Potentially, I'm not really. I'm not.
But I still want an answer. Is it feasible that it can be thermogenic gas?
They don't think that the pockmarks that are in Belfast Bay are thermogenic in origin because they never protrude below the unconformity, the Pleistocene unconformity. So therefore, they have to be at least 11,000 years old, and they think the source of the methane was from that coastal wetland deposit, and that would be shallow water. That would be anaerobic decomposition, not thermogenic gas.
Okay, but keep pushing. Is that region an area that has a potential for thermogenic?
Yeah, there's faulting in that area.
Well, it's also, that whole North Atlantic region actually has a great potential for deep gas.
Okay.
Can I ask a quick follow-up question on that? Or is there a similar figure like this that says where we have good surveys, there are no pockmarks?
Oh, there's a lot of, well,
Like there are
Yeah.
blank areas there, but sometimes we don't have any data there, so we don't know. But is there a consistent pattern of where we don't see pockmarks?
yeah.
I mean, maybe that's just too open-ended of a question. You just may not have surveyed there. They might be.
In areas where they have, in estuaries in the northeastern Atlantic, there are bays which exhibit natural gas and the underlying sediment and no pockmarks form. So is that kind of what you're looking for?
Yeah, just like on the west coast of South America, there are no
Yeah, but you've got.
pockmarks. But
You
is
got
that
the
when
Amazon River, you got the Maracaibo River.
Yes, but what I'm wondering
Orinoco.
is, if you have a bunch of surveys along
Yeah.
that coast, you could say there are no pockmarks here. Or you could also say, we don't know because we don't have enough survey there.
I don't know
I'm
which
wondering-
regions have been surveyed and they
Okay,
have
that's what I'm wondering.
pockmarks. Yeah. Kevin?
We have 3 questions from the internet. And
Wow.
first one comes from Shahak.
We're just about out of time.
Sorry, Shahak. Okay, he asks, it's kind of a 2-part question. Is the sediment cohesiveness dependent only on the electromagnetic properties of the sediment, or is there biology in the sediment that increases the cohesiveness?
Most likely, the biology is going to increase the cohesiveness, and we pulled up biological matter when we took our grab samples, so that's most likely acting to cohere the grains together.
Okay.
Do you know what fraction is organic?
I don't.
How long did it take you to burn off the organics and the hydrogen peroxide?
Well, I only used 3% hydrogen peroxide, but it took 2 months, which is an extended period of time.
Okay, just as a follow-up, Shahak sent a frowny face. But next question comes from Megan Wengrove, and she says, it looks like the sediment resuspension in the northern pockmark along the rim corresponded to the time when you had a 0.3 degree temperature rise. But in the southern pockmark, the resuspension occurred during times of the tide. Do you have an idea why the difference between the two? Or why temperature and corresponding velocity change would affect the resuspension?
Okay, hold on. Okay.
I can repeat it if you want.
Okay. Yeah, can you repeat that again?
Sure. It looks like the sediment resuspension in the northern pockmark along the rim corresponded to the time when you had a 0.3 degree temperature rise. But in the
Well-
southern pockmark, the resuspension occurred during times of the tide. Do you have an idea of why the difference between the two?
I see that at the center, it corresponds to the oh,
She's thinking of the
Yeah.
Shields parameter
Yeah.
plot. That one.
Okay.
That one.
Would only be the horizontal flow, horizontal stress. I think that the temperature change was due to the vertical velocities acting to mix the water column, and that's not a factor of the estimated shear stress. So I don't know if there is a direct correlation between the two. Would be my thought process.
Okay, yeah, the second part of her question is, or why temperature and corresponding velocity change would affect the resuspension, but are you saying that there's no correlation between temperature and...
Well, we observed a gradual rise in temperature over the southern pockmark, and it's still periodic exceedance of the critical. I don't think temperature is influencing when we see sediment.
But what are temperature variability or density variability a sign of? So if you see a change in temperature or density, what is it telling you?
Mixing.
So if you have more
Mixing, there will be more turbulence. So there would be
and if there's more turbulence, then there's more.
stress.
So they could both be responding
Okay.
to the same
So it could be a
thing.
signature of the enhanced mixing.
Okay. The
Okay.
third question from the internet is from Miss Fandel, and she asks if pockmarks are found in fresh water.
Yeah, they are, Mom. They are. They're found in Lake Champlain in Vermont and Lake Rutwadi in New Zealand. So, yes.
Okay, I think we're going to have to cut it off here at this point. It's a subtle hint to rename Belfast Bay.
I know.
However, although they do,
It's
you
not
didn't
my
discover the pockmarks, you might be able to rename those. We have them.
Maybe I can
marked
just
in.
name the ones I said.
One Christine, one Fandel. Okay, so thank you very much.